So can you tell us a bit about who you are?
Yeah, sure. So my name is Chris Limbach. I'm currently an assistant professor at Texas A&M University, which is in College Station, Texas. I'm in the aerospace engineering department, and I both teach and perform research here at the university. My lab group is the Laser Diagnostics and Plasma Devices Lab, and we have about 10 graduate students and undergraduate students with various backgrounds. So it's a very interdisciplinary group. There are students who have a background in aerospace engineering, mechanical engineering, even physics. And we come together to try and use basically applied physics, so optics, laser systems, to try and solve problems in aerospace engineering, mainly having to do with fluid mechanics. And so, we'll get into this, I'm sure, throughout the interview. We have some programs ongoing with NASA, the Air Force, Army, and Navy to try and understand hypersonic flows and apply new diagnostic techniques, which maybe we'll talk about. And then also understand how plasmas behave. So we're talking about ionization. So the sun, for instance, is a plasma. It means that the electrons are pulled off of the atoms and kind of freely floating, right, in the solar environment. In the same way, we can produce plasmas here on Earth. Lightning is another great example. And so, I've been here at Texas A&M for about 4 years now with my research group. But I got started. The question was, who am I? Give some context. I got started. I grew up in Milwaukee, Wisconsin. I lived there until I went to college. And from a very early age, I was really excited about just the universe, right? Learning about space, learning about where our place is, within the solar system, galaxy, the whole thing, and really how the universe worked. And so I was very interested in kind of physics. And I remember, really wanting to, get that first telescope to kind of look at star systems, galaxies, just see what was out there. And so even as a high school student, I went to University of Arizona has this astronomy camp, which I would recommend for anyone interested in astronomy. It was run at the time, I'm not sure if it still is, by Professor Don McCarthy, a wonderful person, wonderful human being. And you go up to Mount Lemmon there in Tucson and actually do some observing with the telescopes they have on Mount Lemmon. And that was just an amazing experience and got me really excited about astronomy, really excited to go to college and then study, the universe and physics. And so I went to the U of A and double majored in astronomy and physics. There's a lot of overlap between the two programs. And then at some point, I decided that rather than observing the universe, I wanted to send things out there and be part of understanding how we get space probes, how we fly hypersonic speed through our atmosphere, and how we can kind of reach for the stars in terms of our technology. So I switched to aerospace engineering, and the rest is history. So I've been doing that ever since.
Mm-hmm. And so, what are some of the diagnostics that you do on gases and plasma?
Sure. Yeah. So I guess getting into that, I've been working with lasers and optics for a long time. As I mentioned, my background is in physics and astronomy, and especially in astronomy, right? Optics plays a very integral role because one of the key ways we observe, things out in the universe is with electromagnetic radiation, right? So, most of the telescopes I think people are familiar with are visible telescopes. So it takes light with a wavelength from 400 to about 700 nanometers, so stuff you can see. People do astronomy in the infrared, in the ultraviolet, radio waves, millimeter waves, basically any electromagnetic spectrum you can imagine. It's used to observe the universe. And what we deal with in hypersonic flight is fundamentally the same stuff, right? We're talking about atoms, molecules, et cetera. And so we use those same instrumentation, right, to observe electromagnetic radiation, but also we can then send in electromagnetic radiation into our fluid flow, our gas flow, in order to interact with it in some way, to try and understand what's happening. And so in terms of diagnostics, what that is referring to is simply measurement technology, right? So throughout history, the ability to measure something new, right, has led to a lot of scientific progress, right? So the invention of the microscope, the invention of the telescope, allow us to see things that are previously not observable, right? And so the whole field of diagnostic development or diagnostics for hypersonics and aerodynamics is to, number one, generate some new ideas with how to measure what's happening in a particular flow environment. And number two, to then apply that and try and understand, use that to understand some flow phenomena which we don't understand very well, right? And so the question was, what are the, what was the question? What are the diagnostics
Yeah,
that
what are the
we apply? And it's really quite varied. So what we're trying to do, right, is measure something about the gas that's flowing through, let's say, a hypersonic environment. So you can think of this as, a simulation in our wind tunnels of hypersonic flight, or a simulation of the space environment and some kind of thruster, a ground simulation of, let's say, reentry flight, right? And you have plasma being formed behind that bow shock. And we want to go in and figure out, what's the, velocity field? How are those fluid particles moving around the vehicle? How is the gas composition changing? We're breathing nitrogen and oxygen, right? But in these hypersonic environments, especially at very high speed, you can get chemical reactions occurring. You can turn the air into a plasma, so electrons get ripped off. And we want to develop ways or methods of measuring, right, quantitatively, putting numbers to, what fraction of molecules have, dissociated into atoms, what fraction of atoms have then become ionized to form plasma. And so to do that, we use a number of different techniques or diagnostics. The simplest is probably just looking at optical emission, right? So in the same way that, the sun emits light, same way that, aurora, for example, is are produced by excitation of oxygen in the upper atmosphere. In the same way, in these very intense hypersonic, flow environments, you can get excitation of the gas itself, meaning that those molecules really have a lot of energy and are able to emit light. And so we can collect that light. This is called emission spectroscopy. We can collect that light and then analyze how much light we get as a function of wavelength, right? So at different wavelengths, we get different amounts of light, and encoded in that spectrum is information about what emitted the light, right? What type of molecule, what type of atom. And so then we can understand better, the composition of the gas. So that's one diagnostic. I won't go through it too many, but I want to highlight just a couple. A key one has to do with light scattering. So this is something that I think everyone is familiar with. The sky is blue, right? Why is the sky blue? Because the radiation from the sun passing through the atmosphere is causing the atoms in the air to behave like little antennas. So the radiation from the sun interacts with the atoms. It causes the electrons in the atoms to kind of slosh around back and forth, kind of vibrate, if you will, in the same way that your antenna, like on a transmitter for like a radio station, for example, or the antenna on your walkie-talkie or your phone, it vibrates a little bit, right? And that sends out a wave, electromagnetic wave. And so the blue sky is basically every molecule acting like a little antenna, sending out radiation, and that antenna is being driven by the sun. And so we see that light, we see the blue sky. This is called Rayleigh scattering. And we can do the same thing in our wind tunnel facilities. So we can send in light. In this case, we're using a laser. Send in laser light and shine it through our flow, our gas flow. And we can actually then see the structure of that flow because different parts of the gas, have different density. There's more or less gas, so more or less little antennas which are sending light out. And so we can actually visualize, what that flow structure looks like. And we can do it very rapidly. So we can do very, very high speed imaging of that to really understand what's happening on very short timescales. And so, so that's one more. And I'll just add that we can do the same thing with plasma. So in the plasma, you have these free electrons just like floating out in the gas, right? I'm using gas and plasma interchangeably, meaning that just the particles are very far apart, they can move around. And so the electrons are floating out there. And so when the electromagnetic radiation, for example, the solar light or our laser light comes through, again, it oscillates the electrons and they behave just like an antenna, just like the current inside of your transmitter, radio transmitter, except that they emit the radiation at optical frequencies that you can see. And so then we can collect that and analyze that. And the most beautiful thing, one of the most beautiful things about physics is, right, it gives you some surprises now and then. And one of the really surprising and beautiful things I found is that encoded into that light which has been scattered by both the molecules of the air and the plasma, encoded is information about what is happening in that gas. It's unbelievable that it's true, but we can actually analyze the light in the same way, looking at different wavelengths. We can analyze it and determine, the temperature of the gas. We can determine how many, electrons there are, how many atoms there are in the gas, and we can determine its velocity as well using the Doppler shift. So frequency shifts depending on whether the gas is moving toward or away from our detection system. And so it's really quite amazing. And the physics and optics is what makes it possible for us to do that. And it's just really exciting. And that's just a snapshot of a few of the diagnostics that we use to try and understand fluid flows and plasmas.
Mm-hmm. And so what are these diagnostics for?
Yeah, that's great. So great question. As I mentioned, there's kind of a twofold motivation for diagnostics and developing diagnostics. One is to develop a new way of measuring something, or measuring something new, preferably, or measuring it better. And then the second point is as a tool, right? And using it as a tool and actually applying it to understand a certain type of fluid flow, right? And so right now, so why are we using these diagnostics? It boils down to, I think, more specific questions, right? Of in a given test, right? So we have wind tunnels, various facilities to simulate a high-speed flight. In a given test, what are we hoping to learn, right? And what we learn is motivated by ultimately, what NASA is charged to do, what the Air Force and Navy are charged to do, our sponsors, essentially what they are charged to accomplish, And so that's where the motivation comes for many of these studies. Now, one of those motivations is understanding ionization. And so basically the tearing off of electrons in these high-speed flows. Mm-hmm. And there are multiple motivations for that. Number one, thermal protection systems, right? So when you come in from orbit, right, and you have a reentry capsule, mm-hmm. you have intense, heat, intense high temperature air interacting with the surface. And so you need to specially design that surface and understand how heat is flowing from the gas to the surface. And chemistry plays a very important role. So the shock, I think most of your viewers may be familiar with the shock. So it's an intense, mm-hmm. abrupt change in the flow pattern, right? That shock can really cause a lot of chemical changes in the air, including ionization. And what happens between the gas and the surface, it matters a lot what kind of composition you have, whether it's a very strong plasma, weak plasma, certain molecules or atoms, etc. And so in order to design that thermal protection system, you need to understand and be able to predict, what the flow composition is and how much plasma you're producing. And so one of the motivations for these diagnostics is to use some of our very unique facilities we have here at Texas A&M that can produce these conditions, and to use our laser systems to get a better understanding of the chemical transformations which occur in these kind of reentry type flows, namely the ionization and also the dissociation of the gas, because that impacts reentry. As another example, so that would be a motivation for both the Rayleigh scattering, the Thomson scattering, as well as the emission spectroscopy and other diagnostics. That helps us understand what we're seeing in our experiments and quantitatively comparing to models. Just to give you one other example, we're trying to understand our ability to predict flows in scramjets, right? So scramjets are propulsion systems that allow us to fly in the hypersonic regime, which is Mach approximately 5 or greater.
Mhm.
And it allows you to do that by being able to burn gas supersonically, or sorry, burn fuel supersonically. And one of the important aspects of the scramjet is that there's actually no moving parts, in the sense that the structure itself of the aircraft compresses the air before you burn. Right? So in your internal combustion engine, there's the piston compresses the air, you inject and burn, and so forth to derive power. In the scramjet, nothing's moving, but the motion of the vehicle compresses the air. And the first compression that occurs is called the inlet. Right? It's where the air goes into the flow path, the combustion flow path. And we're working with the Air Force and Boeing to test our models, our computational models of how well can we predict the flow coming out of that inlet. And so we're using diagnostics to make measurements in a type of geometry in a wind tunnel model that we're designing, and we're trying to understand, what is the flow structure quantitatively, what is the velocity flow pattern, and compare that with the models, and we'll see what we find. So that's really, what are these for? They're to really solve problems and understand the fundamental flow physics in order to improve our predictive capability, improve the ability we have as aerospace engineers to design systems, right? Flight systems that we have high confidence in.
And also, so what is a non-equilibrium plasma?
Yes. So non-equilibrium. So I think to talk a little bit about non-equilibrium, we first have to talk just a bit about equilibrium, right? So and why this is relevant to hypersonic flight and space propulsion. Now, when we talk about propulsion, right? Really, we're talking about taking some kind of energy input, right, and generating thrust. And when we think about the excitation that occurs, right, the deposition of energy into a gas, whether that be electromagnetic energy, chemical energy, energy derived from the flow itself, as in the case of a shock, the atoms and molecules, right, get heated up. What does that mean? It means that there's more energy available to excite those atoms and molecules to be captured in a single atom and molecule. And the temperature, right, when we talk about temperature, it's really giving us an energy scale, right, for an individual molecule. So the higher the temperature, the more energy can be stored or is stored in an individual atom or molecule. And so what non-equilibrium is really referring to is that there are these different storage mechanisms, right? You can think of them as kind of like different bins, right? One bin might be just the motion, right? The motion of the atoms and molecules around. Another bin might be rotational motion of a molecule, right? The spinning. Mm-hmm. Another bin might be vibrational motion. So it's kind of like a little mass spring. And in equilibrium, energy is shared between all those bins. Not equally, but in a well-defined manner consistent with what we call equilibrium. What non-equilibrium is referring to is when the energy is not being shared as evenly, right? So let's say a good example might be that the vibrational motion of the molecule has a lot more energy than you would expect based on all the other apportionment of the energy. And so that's kind of gives you a sense what we mean by non-equilibrium, right? It has to do with the way in which energy is shared between molecules and between different excitations of a given atom or molecule. And so why is it important? The reason it's important is because we can actually see this non-equilibrium apportionment of energy in hypersonic flows and in high temperature flows that are changing very rapidly. And that's certainly the case if you think about a reentry capsule. The gas, just to give you a sense, it can flow over the entire vehicle in much less than a millisecond, right? So there's things are changing rapidly. 1 minute it's in the atmosphere minding its own business at about 270 K or what have you. The next moment it's through the shock and at 10,000 K, and then within a millisecond after that it's all the way around the vehicle and back at some lower temperature but with a completely different composition. So things are changing rapidly. Energy is being exchanged back and forth between these different types of bins, energy storage bins. And so it's important to understand how that process is occurring if you want to predict things like the amount of heating going into a flight vehicle, if you want to predict where shocks are going to be located around the vehicle or in the scramjet inlet for that matter. And so these things are just one important aspect of what you need to take account of when you're thinking about hypersonic flight and also in any type of propulsion system where the gases can be excited and is rapidly evolving.
And how can this improve aerodynamic flow control on aircraft or spacecraft?
Yeah, so I would say that non-equilibrium and non-equilibrium effects are a phenomena which is, I think, distinct from flow control, right? So they're kind of two separate topics. There's a little bit of overlap. And the reason I say this is because you can have non-equilibrium without flow control. And some types of flow control are approximately even plasma-based flow control. Plasma is close to equilibrium, but certainly there are some situations where you can create a plasma which has this non-equilibrium aspect. I don't want to go, get too deep into the weeds here. I think the important part of this question has to do with the flow control, right? So why do we need flow control? What do I mean by flow control? And by flow control, I'm referring to the ability to interact with the flow to control a vehicle, right? Flight vehicle. We're talking about, how do you fly hypersonically and respond to changes fast enough, right, to be able to fly. So just imagine, you're traveling at, kilometers per second, right? So if there's some disturbance, it's not going to be long before the vehicle is, destroyed if you cannot recover from some disturbance. And so you think about, mechanical actuators like flaps on an aircraft. These are relatively slow. We've seen them all, in when we travel by air. They don't move very fast. They don't have to on a commercial aircraft, but you can just imagine they're fairly heavy. You need some kind of maybe motor mechanism, maybe it's some other mechanism, but big things are moving. The advantage of some kind of plasma is that you can create it extremely fast as basically electronics at the speed of electronic systems. And so plasmas, I talked a little bit about plasmas before. We're talking about ways in which we can use electric fields primarily to pull off electrons from the gas in the air, and that creates a conduction path in the same way that you have lightning, right? So when the lightning is generated, right, it's a discharge, so there's charge stored in the atmosphere. comes to the ground, current flows, so that charge flows. Moving charges create a current, and that flow of current leads to some heating, significant heating, it turns out. And so the same thing we can do with electrical circuits, right? And basically discharging a capacitor or some other type of power supply. We can have high voltage. We can use high voltage to create this plasma and create it on demand. So you can say, tell me when to create this plasma, and boom, 10 nanoseconds later, you have a plasma. And so what that allows us to do is it allows us to heat the gas a little bit. Certain types of plasma control systems can actually push the gas a little bit by interacting with the electric field. And so there's different mechanisms by which we can affect the flow, and we can do it on the timescale of electronics. So again, we're talking nanoseconds to microseconds, much faster than a mechanical actuator. And so what we're trying to do with flow control generally, in particular plasma-based flow control, is to interact fast enough and produce effects which are large enough and are cost effective in terms of the energy and space required for the systems. Mm-hmm. And to actually have that be a viable way to do very fast control of high-speed flight systems, primarily for hypersonics.
And how can that same plasma also improve propulsion?
Yeah, so the plasma is a huge topic, by the way. So I don't want to gloss over the fact that there's about I don't want to say thousands, but certainly like hundreds of different types of plasma that you might encounter. Mm-hmm. Naturally produced plasmas, different types of electronic systems that can produce plasma. You can do it with, just high voltage leads, right? Many people might be familiar with, you have grills, right? And the starter button mm-hmm. produces a little spark. That's a plasma. You can produce plasmas with radio frequency waves, microwaves. You can produce plasma with lasers. I've done a lot of work on, you can actually take a laser beam and focus it so tightly that the electric field starts to rip atoms off of the gas in the air. So it's a plasma just floating in space with no electrodes at all. There's tons of different types of plasma. Now, are all of the types of plasma that are out there useful for propulsion? Probably no. Some will be better than others in producing thrust, and in particular doing it in an efficient way. And when we talk about plasma propulsion, we're typically talking about space propulsion, and the important parameters there are specific impulse, which is a measure of how efficiently you're using reaction mass to generate a change in velocity of the spacecraft. Mm-hmm. And then thrust, I think, is how hard you're pushing, right? And there's trade-offs, right, between those two things. And you always want high energy efficiency, because most of the time you're deriving energy input from either chemical reactions, or in the case of plasma propulsion, it's primarily going to be solar or some type of nuclear electric generation. Mm-hmm. And so the plasmas, there's lots of plasmas being explored as potential propulsion systems, and it's not like a one size fits all. Again, it kind of goes back to the application. Like, what does a particular application need in terms of the plasma that produces the thrust? So, for example, a thruster which does station keeping, right, and just needs to keep a satellite in its orbit, in the presence of some perturbations in the gravitational field and other things, that thruster is going to need to be a lot different, probably, than a plasma propulsion system that takes astronauts to Mars, right? Mm-hmm. So different applications, different types of plasma. But fundamentally what plasma does is it allows the propulsion system, and particularly the exhaust velocity of the gas, which is associated with the specific impulse. it allows that to be decoupled from traditional gas dynamics. So in a traditional rocket, you heat up some gas, usually with combustion, expand it through a nozzle, and turn some of that stored energy, right, the heat that you've added through combustion, and transform that into the directed motion of the exhaust, right? Mm-hmm. But you're limited by how hot you can get the combustion to happen, right? And that's a chemical limit as well as a materials limit. And so plasma allows you to avoid all of that, because you can use the electromagnetic fields to accelerate particles instead, right? You now have free charges floating around, ions and electrons, and you can go in to the plasma and use electrodes. You can generate magnetic fields with currents, like a solenoid, for example, and you can cause those ions and electrons to move in such a way and accelerate them to much higher velocities than you could achieve with a thermal, a thermal system. And so that's really the advantage of plasmas, is you're able to circumvent some of the limitations with kind of gas dynamic propulsion systems.
Mm-hmm. So what has been your toughest accomplishment so far?
Sorry, can you repeat that one more time?
What has been your toughest accomplishment so far in your career?
Yeah, that's a good question. Toughest accomplishment. Well, that's a great question. I mean, I think that the PhD work I did at Princeton was certainly one accomplishment, but I think more than that, what I'm probably most proud of right now is assembling the research group I have here at Texas A&M. We have about 5 master's students and 2 PhD students, and we recently had a postdoctoral researcher, Yue Wu, who's now moved on to Metro Laser, which is a company in California that does diagnostics. And it's a very interdisciplinary group, and it's been very important to me to foster a sense of kind of inquiry, like open inquiry, and allowing people to ask questions, right, without worrying about how they're being perceived, and to just share knowledge and what they know, because everyone brings something to the table. As I said, we've got mechanical engineering background, aero engineering background, physics engineering background. Nobody is going to accomplish or be able to know everything, right? And so it's very important to recognize, in everyone, and I think the group has done this, recognize what everyone's strengths are, and to kind of collaborate to solve problems. And so I've been very proud to see everyone come together and work together, and really I'm very excited about the type of team we have here at Texas A&M. I'm also indebted, I have to mention that I collaborate with a number of people here in the aero department and across the university. And in particular, this kind of collaborative atmosphere and group atmosphere has really been helped by the efforts of Professor Richard Miles and Professor Rodney Bowersox, who I collaborate with extensively. And Dr. Bowersox directs our National Aerothermochemistry and Hypersonics Lab, and we have to work together to do some of these amazing things here at A&M, and it wouldn't be possible without the people here. So I think assembling that group of people has been a 4-year effort, and I'm certainly very proud of that.
And is there a big milestone that you're looking forward to in your research?
Yeah, I'd say there is. We have one project that I've been really excited about. I'm excited about all the projects that we have going on here, but this one's kind of out there, and it's funded by NASA. It has to do with space propulsion, but rather than using reaction mass, so basically sending some propellant and combustion products or plasma out the back end, you actually use a beam, a beam of either, people use lasers or particle beams, and basically have a transmitter that sends out the beam, and basically just those particles or photons reflect off the spacecraft and kind of push it.
Mhm.
right? So there's some of your listeners may be familiar with this Breakthrough Starshot, which is a organization dedicated to making laser propulsion possible to take us to the nearest star system. But we have a project with NASA looking at a combination of laser and particle beams. And I won't get into all the details, but it's really exciting because a laser, as you may know, if you played around with like a laser pointer or even a flashlight, same kind of idea, as it goes farther away, it expands, right? And this is called the diffraction limit ultimately. And so any type of laser, eventually your spacecraft's going to be so far away, it doesn't really get any thrust anymore from the laser reflection. So what we've been looking at is where you have a laser and a particle beam, and you can actually have the particle beam act as a waveguide. So like a fiber optic cable, right? So some of us get internet by fiber optic. It channels the light, right? Where you have a higher refractive index. In the case of air or this particle beam, it means where you have a higher density of molecules or atoms. And so we can use the particle beam to kind of channel the light and overcome the natural diffraction which would occur in space. In addition to that, you also have very weak but real forces that cause the atoms to be pulled into the laser beam. And so at the same time, you have the channeling of the light beam, and then the atoms are trapped within the light beam. And so this has never been observed before. Each of these phenomena have been seen individually ad infinitum. This is very well-known stuff. But together, no one has ever seen that before. And for the first time, we've got a source now of atoms in our laboratory, a vacuum system that we're going to be using to test out this idea. And I'm just very excited to see what comes of that experiment. And hopefully we'll get a result that shows that this type of travel is possible. But I'm very excited to see what happens there. It was one of those crazy ideas, and hopefully it turns out to be a reality.
And lastly, what would your advice be to high schoolers and younger generations like me that want to become aerospace engineers?
Right. The advice I would give, well, I don't know. I mean, it's been a long time since I was in your shoes, but I'd say, based on where I stand now and thinking back to, kind of what was going through my mind at the time, I'd say, number one, be proactive and do what you love to do. Don't try to, be someone you're not. Just latch on to what it is you're really excited about and interested in, what you're curious about, and use that as motivation to go out and do something along those lines. Interact with people who either share that passion, or people who are living that passion, and try to get involved in something, either by yourself or with a group. I mean, there's a lot of value in just kind of going outside your comfort zone and trying to make something happen. The second thing I would say is, as you're going through your academic career, keep asking those hard questions. Hard questions that challenge your understanding and challenge the understanding of people like myself, right? So Feynman has a famous saying that if you can't explain something in simple terms, then you really don't understand it, right? And so sometimes, sometimes you can get in a situation where something sounds really complicated, and maybe there's another explanation out there that's more simple, and take that passion and curiosity and look for that answer. And then challenge your own understanding, right? And try and refine the way you understand the universe and what's happening in front of your eyes. And then finally, the last thing I would say is just be imaginative, and ground that imagination sometimes in what you know in terms of understanding about the universe, but really nothing can substitute for just curiosity and imagination in coming up with new ideas. There's a quote from Einstein that imagination is more important than knowledge. And that's partially true, I would say. I think that knowledge is certainly important. It tells us what we know about the universe currently, but in science, there's always a little asterisk, right, next to that, subject to further improvement, right, of our understanding of the universe. And so imagination is very important to, discover that unknown, to improve the understanding, and also to take what we understand currently and come up with something new. One of the best parts about my job is that oftentimes we have a problem or a question, right? We're curious to find the answer, and we have to use our imagination to figure out a way to do that. That might be a new way to do the experiment, or imagine a new measurement we can make, or let's say that something doesn't exist yet to make that measurement. Well, we have to imagine a new system, a new diagnostic system to make that measurement and to do it fast enough or with enough precision. And so I would say every day I use both, the technical knowledge I have, but use it with my imagination to solve these problems. And that's probably the most exciting thing, and why I love this job.
Well, thank you for joining me for the interview, and yeah, thank you for your input.
Yeah, thanks. Thanks so much for inviting me to the interview, and best of luck in your future interviews as well.
All right. Have a good day.
All right.